Hello everybody, welcome to a video on drawing Lewis structures. Today we're going to be going over steps 1 through 6 of how to draw a correct Lewis structure based off of a chemical formula of a molecule. Now, the first step in drawing a proper Lewis structure is to arrange the atoms around the central atom. So within your molecule, you should be able to identify which atom is going to be in the center, have the most connections to the other atoms. Now, the central atom is usually the least electronegative and has the highest bonding capacity. As you can see here, this is just an electronegativity chart that you could go off of in order to make your assumption. Now, the second step is to determine the total number of valence electrons in the molecule you're looking at. So, for example here, let's take a look at carbonate. We have CO3 2 minus. Now, to determine the total number of valence electrons, we break it down by each atom. So we have carbon, and when you look at carbon, carbon always has 4 valence electrons on it because it's the 6th element on the periodic table. And so we have carbon with 4 plus oxygen, and oxygen has 6, and we have 3 oxygens, so we can go 3 times 6. And here we have a little subnote saying if negatively or positively charged, add or subtract electrons. And we know that if we have a molecule that is negatively charged, it means that it has more electrons. And if it's positively charged, it means it has less electrons. So we have a charge of 2 minus on the carbonate, which means we're going to add 2. So if we sum this together, we will have 24 total valence electrons. Next, for our third step, we'd like to place a pair of bonded electrons between the atoms to give a single bond. So I'm just going to look at methane for an example. So we'll go for methane, which is CH4. Now we can get a central carbon, and then we have 4 hydrogens around it. And it says here to place a pair of bonded electrons, so we can go 1, 2, 4, 5, 6, 7, 8, filling the octet of carbon and the hydrogen, and we can move from this and draw these bonds as a single line. Now, one way that I like to view it is within this bond here, the single line, I like to see the ends of the lines being one end and 2 ends, and I like to count that as the total number of electrons present. So instead of seeing 1 line, 2 line, 3 line, 4 line, think that each line has 2 electrons present at the end of each bond. So if there was, for example, a double bond here, then that would have another 2 electrons on it. For our fourth step, we have to begin with our terminal atoms. So terminal atoms are typically hydrogens or halogens, because if you look on the periodic table, hydrogens have 1 electron in their valence electrons, and halogens need 1 electron. So beginning with those, we will want to add enough electrons to complete the full octet. So let's look at our example of methane with CH4. So we have 4 hydrogens, so our terminal atoms will be on either end of the carbon. So we'll have the carbon in the center, hydrogen, 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 hydrogen. So what we're doing here is we're actually the reason why we're placing them in this orientation is because we're completing carbon's octet. Carbon naturally has 4 valence electrons on it, but if each one of these hydrogens is going to have an electron themselves, then the carbon in the center will go from having 4 electrons to having a full octet of 8 electrons. And the word octet is derived from the prefix octa, which means 8. All right, so for step 5, it states that if we have leftover electrons after counting our total valences, then we need to place them on the central atom. So if our central atom is in the 3rd period or more, so if you look at your periodic table and know that the period counts the rows, not the column, if your atom is in at least the 3rd period, then you can exceed its octet. So for this example, we're going to be looking at xenon hexafluoride, so XeF4. So if we counted the total valence electrons, we'd have Ve equals xenon has 8, So we'll go 8 plus the 4 times 7 to get us to 36. Now, when we draw it out, we will have xenon and then 4 fluorines, just like we did before. 1, 2, 3, 4. We have to complete all the octets. Right, but then if we count this up, we have 8 here, 8, 8, 8. We have a total of 32. We have 4 electrons that we haven't accounted for in this drawing. So we need to take the xenon, which is our central atom, and we need to add 4 more electrons onto it. Now for the last and final step, once you've checked your valence electrons total, and you find that the central atom has an unfilled octet, then you should add double or triple bonds in order to fill this octet. So we're going to look at a quick example of CO2, or carbon dioxide, CO2. So if we know that carbon is going to be our central atom, and if we go oxygen and oxygen, quickly I should actually count my valence electrons, which is 4 plus 2 times 6, which will be 16. If we go 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6. So here we have 18 valence electrons, and looks good. But we notice that carbon here, carbon has an unfilled octet. So what can we do? We can add double or triple bonds. So if we take this carbon and we say, okay, instead of having single bonds, if we give it 2 double bonds on either end with oxygens 1, 2, 3, 4, 1, 2, 3, 4, everything still has a full octet here. But if we count the electrons, we can go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. And you see that the total number of valence electrons lines up and everything here has a full octet. So this is the most valid structure for carbon dioxide. And here we just have a culminative image of all 6 of our steps, each color-coded. You can take a screenshot, pause, write this down if you'd like, but this is basically just everything we went over, minus the examples.